Yeah, the presentation is about like the title says, hydrogen as a fuel for heating processes. And I would like to sketch some of the challenges we are currently facing when we convert natural gas burners to hydrogen burners. But before going into great detail, I would like to give a short introduction. Let me see. Yeah. A short introduction why hydrogen is becoming more and more popular. Of course, what we all see around us is that the electricity produced from solar PV and wind increases, of course, substantially. All around us, we see more wind farms, solar farms. And of course, that puts a lot of pressure on the current capacity of the power grids. Some of the grids, especially in the north and in Holland, are already not often disconnected, or we get issues with too much sustainable energy, which is entering the gas grids. And one of the solutions is, of course, to produce a part of the electricity produced, convert that to hydrogen via electrolysis. And of course, that's a very good way to reduce the capacity for the power grids currently, but also for the future. A lot of processes also need molecules, so this is, in our opinion, a very effective way to do so. What we also see is, for example, in the Netherlands, we have a very big network, gas network present, and we can convert part of the network to, for example, dedicated hydrogen pipelines. And these pipelines, yeah.
Could you switch to full screen, please? Because
we are not full screen. Okay.
No, we are not. We are seeing this as how do you say, the presenters probably. No, but we are not able to see the full screen.
Okay, that's strange. In my, it was good before?
No, now we see the PowerPoint.
Yeah.
I think you need some presenters view.
Yeah, I did, but
could you press F5 on your laptop?
Yeah. Is this good now or not?
No, it's still in the editor mode.
Okay, but in my screen, it's on.
I think if you go to the presentation and then at the top there is an option display settings, and you click there, and it allows you to switch between the presenter mode or the presentation mode.
Where should I go then? That's
if you go to the presentation mode.
So F5, I think.
Yeah.
As you did before, you went to the presentation mode at the bottom, or wherever you.
Now, what should I press then? It's.
Yes, at the top there is a display settings. If you click on that.
Yeah.
Oh yeah. All the way up, Sander.
Yeah.
At
in the middle.
The display setting. Yeah.
Yes.
Here, I should go.
Yeah.
Oh, display setting. Yeah. And then presenters.
Exactly.
Yes.
Oh, okay, great.
Yeah.
Is it better
now it's great.
Yes. Now it's. Yeah.
Thank you.
Okay, great. Thanks.
Thanks.
No problem.
Yeah. Okay, but so basically, there are a few options, of course, when you produce renewable hydrogen from electricity. That's put it in the existing gas grid and blend it into, for example, the hydrogen, the natural gas, so that you get a mixture of hydrogen and natural gas, which is going to the end users. But another option, and that's in the Netherlands, one of the preferred options is to make dedicated hydrogen pipelines, so that we have a dedicated hydrogen grid. If you look, and of course, the natural gas grid is already connected to the industry and also built environment. So those two sectors are in that sense already perfect to transfer to hydrogen. But also, of course, other sectors are, of course, the mobility, the fuel cells, which you can use hydrogen in. That's also an important candidate. But in this talk, we mainly focus on the industry. if you look at the industry, why is hydrogen there important? Well, in our opinion, hydrogen as a fuel is one of the fastest routes to make the industry more sustainable. Especially when you, for example, look at the high temperature industry, like for example, glass making, baking stones, or the ceramics industry. They often need molecules to get those high temperatures. And of course, when you use hydrogen, you do not have to change your process drastically. Well, if you switch to electricity, which might also be possible, but then you have to buy a new furnace, for example, or you have to make other big capex investments. Another advantage, like I already mentioned, the national gas grid is already connected, so you also there the investments are relatively low. Of course, you have to do something, but it's cheaper than expanding the electricity network. Then you need huge amounts of extra electricity. And also for the industry, that's often clustered, and that's also an advantage because then you can transfer some clusters to hydrogen. While if you look, for example, at the domestic market, there it's more complex to make the switch to hydrogen. And it's also possible, but the industry, it makes it a bit more easier because it's often clustered. And of course, if you look at the price, gas transport is much cheaper than the transport of electricity. So that are all quite benefits of the use of hydrogen instead of electricity. And that does, of course, not mean that electricity is not a good way. When you, for example, with heat pumps, you have a high efficiency. There you should, of course, use electricity. But there are a lot of processes where you better can use molecules. That's often forgotten, and people only talk about electric sustainability and then talking about electricity, but combustion will be in the future, in my opinion, still very important, especially in the industry. Another advantage of the industry over other sectors is the economy of scale. For example, if you take a glass factory, in the Netherlands, we have around 8 production locations. And they use in total 200 million cubic meters of natural gas, so that's about 600 million cubic meters of hydrogen, billion cubic meters of hydrogen. And that's the same as all the line buses in the Netherlands, even more. The 7,500 line buses equals to around 600 billion cubic meters of hydrogen in energy-wise. So it's much easier to do the fuel switch in the industry than converting all line buses. Of course, you should do both, but it's just an example of the economic scale when you use hydrogen in the industry. If you look at the cost of hydrogen, I'm not a specialist in cost, but always everybody asks, okay, what is the cost of hydrogen? And that's, of course, an important factor. If it will be a success in the future, yes or no. If you look at the prices now, if you look at the figure here below, and what you see that the price of hydrogen per kilogram is around $5 US, maybe a bit cheaper. But what we see, at least expect, is that price will drop around 1.6 US dollar per kilogram in about 2030. So that means that it reaches the point of break even with hydrogen produced from steam methane reforming, gray hydrogen we call that. And then it will also compete with other fuels because the CO2 tax will increase. So we think that looking at the pricing, that also around 2030, hydrogen will be more and more attractive as a fuel. Challenges, of course, there are a lot of challenges when you want to use hydrogen in the industry. And therefore, I think also in the next decade, we as combustion engineers will have a lot of work to do. And then one thing is, of course, the challenge availability of hydrogen. Currently, there is not a lot of hydrogen. We do quite a lot of pilot projects, and then always the question is, how do we get the green hydrogen for the pilots? But then after, at the end of the day, we use gray hydrogen. Unchanged product quality, that's something the industry wants. If you switch from natural gas to hydrogen combustion, then you have to deal with the changes in combustion properties. For example, changes in temperature, flame temperature, flue gas composition is different, flame radiation is different, and that might also impact, for example, product quality. if you have direct heating, but it also might, for example, impact your refractory material. So there's work to do. And of course, the industry also would like to have a simple and cost-effective implementation. And what we also, we talked a lot with the industries, and part of the industry also says, okay, in the transition phase, then there's not enough hydrogen, green hydrogen available. So what we would like to do then is blending hydrogen with natural gas. And then when there's enough hydrogen available, then we would like to make the fuel switch completely to 100% hydrogen. So one of the solutions is to develop burner systems or engine systems which can cope with natural gas, but also blends with hydrogen, and at the end just switch to pure hydrogen. So then you basically have a no regret solution if you implement that in your factory, for example. And this also offers great benefits with limited investments. And that's basically what we have been working on together with the industry over the last years to develop burner systems that can cope with a wide variety of different gas compositions. If you look then, like I mentioned, the challenges, the changes in combustion properties, just to give you a flavor of some differences in the properties. Of course, the air demand is completely different of hydrogen. It only needs half an oxygen molecule to have complete combustion, while, of course, methane, natural gas, needs 2 molecules of oxygen. But we also see, for example, that the upper explosion limit is completely different. Hydrogen burns quite. You have, when you have 75% hydrogen in your air mixture, then you even get ignition. So, and that's only 60% for natural gas, at least does natural gas. Ignition energy is much lower. We see changes in the Wobbe index. The calorific value of hydrogen is a factor of 3 different than natural gas. And all these things, and the density, of course, which is very important, is much lower. Now, all these items affects the combustion properties, but also just the physical properties. If you look at, for example, the density, then we have, for example, gas transport, and your density decreases with a factor of 9. That means that you need much more compressor power for your system, distribution system, but also your centrifugal compressor will have a huge problem because they will not get the correct compression head. And all these issues we have to deal with, and we have to find solutions for that. Also for safety, the safety rules will change when you use hydrogen due to the changes in the ignition energy explosion limits. And when you combust, of course, hydrogen, then you also will see, as you see in the lower table, changes in the flue gas composition. You have much more water vapor, no CO2 anymore. And that's, of course, will also impact the heat transfer, but also it can also impact the quality of your product. For example, if you make glass or you're producing bricks for the in the industry. And one of the issues, of course, what we are facing is NOx emission when we switch to hydrogen, which of course depends on the burner type and the temperature regime where you are in. But in general, this is just an example. On the left-hand side, you see a natural gas, that's the red line. And if you switch to hydrogen, then you see higher flame temperatures. And when you have higher flame temperatures, then also, of course, the thermal NOx emission will increase. As you can see on the right-hand side, you see the red line again for natural gas and the blue line for hydrogen. And then you see an increase in the NOx emission when you switch when you switch to hydrogen. And that's, of course, directly related to the flame temperature. You have simply more thermal NOx formation above a certain threshold temperature. And that's also what we see back in our measurements. When we switch to hydrogen, we often see more NOx emission, which is related to the flame temperature of hydrogen. If you look at efficiencies, this just to give you an impression, as you can see here, then what you see here on the right-hand side, you see the thermal efficiency. And what you see if you have high temperatures, when all the water vapor is still in your flue gas, then you see much lower efficiencies for hydrogen combustion based on the thermal efficiency. around 6% points less than for natural gas. And that's of course the reason for that is that you have much more water vapor inside of your flue gases. And if you do not condense them, then of course you have more latent heat in your flue gases, which you're basically simply throwing away. So that's a waste. So what you should do always is condense your flue gases and get that the latent energy also out of your system. And then what you see on the beginning for the low temperatures, that the thermal efficiency is more or less equal for hydrogen combustion in comparison to natural gas combustion. So that's one of the things always to take care about. You always should bear in mind if you switch to hydrogen that the latent energy is different from natural gas. If you look at other aspects, of course, when you switch to hydrogen, that's one of the very important aspects is the flame radiation, the heat radiation flux, which is coming from the flame. That's important, for example, for heating the product. The radiation transfer is very important. And that's related, of course, to the emission coefficient of the flue gases and also the flame temperature, as you can see in this equation. And what we always do, we have developed models within DNV together with the universities. And just to give a very simple overview, what we do is we calculate the flue gas composition, and that changes, of course. And then we calculate the emission coefficients via different models, and then also the flame temperature. And then you can calculate how much radiation is coming from the flame. This is, of course, a simple example. The next slide, I did some calculations just to give you a flavor. On the left-hand side, you see the adiabatic flame temperature as a function of the hydrogen percentage in natural gas. And what you see, of course, is that the adiabatic flame temperature increases when you switch to hydrogen combustion. And you, in the figure in the middle, you see the changes in flue gas composition that radiates. So the hydrogen, so the water and the CO2 molecules, they radiate both, which are very important for the heat transfer via radiation. What you of course see is that CO2 drops, but the water fraction increases, which compensates partially the radiation losses from the drop in CO2. And ultimately, on the right-hand side, you see the combination of flame temperature and changes in gas composition. And then what you see in this very simple calculation, that the heat flux increases when you increase the amount of hydrogen in natural gas based on this simple calculation. It's an increase of around 25%. We also did a lot of flame radiation profile measurements, and there we often see not that much differences between a natural gas flame and a hydrogen flame. And that's also because you have to take into account, of course, the shape of the flame that's also changing a little bit. But in practice, we do not see a lot of changes, but if you look at these calculations, you see a small increase. That's mainly due to the increase in adiabatic flame temperature. The thermal input, which is also very important for burners. As an example here, if we, for example, look at the density, that's a picture on the left-hand side, then if you switch to hydrogen, you see a huge decrease in the density. And if you keep the same pressure drop over the fuel nozzle, as you can see in the equation here, then what happens, of course, if the density decreases with a factor of 9, then the fuel flow increases with a factor of 3. And that's what you see back in the picture in the middle. Here you see the fuel flow, the blue line increases when you add more and more hydrogen. You see an increase from 30 to 90, so a factor of 3 increase. Of course, the calorific value decreases at the same time. When you switch from natural gas to hydrogen, that's also decreasing with a factor of 3. So that basically compensates the amount of energy that you supply to the burner tip. And that's what you see on the right-hand side. You see two graphs, that's the Bob index and the thermal load of the burner. And you see the same behavior. So if you add hydrogen up to 90, up to 60%, then you see a small drop in the amount of energy flux. And then after 60, 70%, it increases again, at least for Dutch natural gas. And ultimately you see a change of about around 10% in the energy flux, which is fueled by the burner tip. So that's not that much, but still for a lot of processes, that's too much. So there we always recommend to add a fuel adaptive control system in order to keep always the energy input to the burner constant. And this is of course related to the Bob index. Another aspect is changes in the air demand. When you add hydrogen to natural gas, of course, also your air demand changes, and therefore also your amount of oxygen in your flue gases can change. I will show some pictures later on. And we also always keep that constant while changing the amount of hydrogen in natural gas. Another aspect which is changing, and that's of course the burning velocity. What happens if you add hydrogen to that natural gas and also to natural gas, that what you see is on the picture on the left right hand side at the bottom is that the flame velocity increases, the laminar burning velocity. Up to 60%, you do not see that much difference, but after 60% hydrogen, then it's more from chemistry wise, and the real hydrogen flame, it becomes a real hydrogen flame. And then you see an exponential increase in the flame velocity. And this can cause, for example, flame flashback into your burner ports or overheating. In the picture on the right hand side on top, you see, for example, here a natural gas flame, which is nicely stabilized on the burner. However, if when we add hydrogen, then we see that the burning velocity increases and the flame crawls inside of the burner tip, which is causing overheating of the burner surface. That's something you do not want. And if you add more hydrogen, then you get complete flashback of the flame back into the burner tip. So that's always the issue with pre-mix systems. So the systems where you have fuel and air are pre-mixed before you combust it. If you look at other type of burners and nozzle mix burners, that's our non-premixed burners. So air and fuel is supplied separately. There we see different behavior in our flames, at least we studied. For example, an important aspect is again the density. What we often see is that the fuel jet, which you see here, is the angle of the fuel jet becomes wider when we add hydrogen to the flames. And that's of course due to the difference in density. The density of hydrogen is much lower than that of methane. And then we see often that you have much more air entrainment already at near the burner, near the nozzle, so in this area. That means that you already get combustion or closer to the burner surface. And that also can cause overheating, for example, of the burner block. But another aspect which is quite important, that's the momentum flux. Momentum flux is basically the density times the velocity of the jet squared. That also says something about the flame length. And that's also something you can calculate, and that's you see on the picture on the figure here, the momentum flux, and here you see the amount of hydrogen, and you see a slight increase and then a drop. But if you compare pure hydrogen, the momentum flux of pure hydrogen and natural gas, and you do not see that much differences. So that suggests also that the flame length might not change that much as you would expect based on, for example, only the flame velocity, which you see on this right-hand side. So if you switch from natural gas to hydrogen, then you see that the fuel velocity increases, of course, with a factor of 3 when you keep the energy density constant. But that does not impact that much on the momentum flux because also your density is changing. So basically, what do we expect when we add hydrogen to natural gas for these diffusion type of burners? Basically, what we expect is an increase in the angle of the jet, so that the flame zone crawls closer to the burner surface. But we also expect to see not that many changes in the flame length, but it also depends, of course, on the burner. And later on, we will show some examples. If you have a look at a very simple example, that's you can see in this picture. What we did, we developed some burners for hydrogen for domestic use. And on the right hand side, you see a very nice stabilized flame on top of the burner. So this is basically a tube which contains small holes in it, and hydrogen is coming out of the jet, and it mixes with air from the surroundings, and then you see a nice stable flame with hydrogen. But if you look at methane, then you see that the gas is not very well mixed in the beginning. The explosion limits are much smaller than for hydrogen, and then you see combustion much farther away from the burner itself. So here you already see that if you switch to hydrogen, that most probably your hot flame zone is coming more closer to your burner, and that's also what we see in practice for the burners we studied thus far. So there are some challenges when applying hydrogen for industrial burners. Like I already mentioned, the NOx emission can change. Also changes in heat radiation, convective, and of course radiation, both. We can get overheating of the burners. We can have flashback. But it's very important to mention that the effect strongly depends upon the type of burner which is installed in the industry. If you look at, for example, the ceramic industry, they have pipe-and-pipe burners, high-speed burners. The steel industry also uses, for example, flux burners. Glass industry uses flat flame burners, pencil burners, which are often pre-mixed, but also oxy-fuel burners. And all these burners respond differently. And if you look at the paper industry, and hot water, they often use this forced draft burners. Very roughly, you can divide these two burners into two categories, and those are premixed burners and non-premixed burners, which have complete different behavior, of course. If you look at the premixed burner, what I already mentioned, when you have the fuel and air are premixed before you combust it, there you see the risk of overheating and flashback, which is an issue. And what we did for these type of burners is the following. If you look at the graph here, you see, for example, if you have the burner designed for natural gas, in this case, then your design point is here, it's the green dot. So it is for natural gas, it has a flame velocity of around 40 centimeters per second. So there we have stable combustion for the most type of burners. But if you then switch, for example, to pure hydrogen, then you go the line up, then you go to around 200 centimeters per second in this case. And then you have a big issue because then you have flashback. So what we did for these couple of these burners is we decreased the equivalence ratio. So we increased the amount of excess air. And if you do simply calculate the burning velocity, then around 0.4 equivalence ratio of 0.4, you have the same combustion speed as for natural gas. And then you should not face any flashback. Now for the appliance we studied thus far, then we still have flashback, but if we decrease it to around V is 0.3, then we have stable combustion. So that's one of the solutions you can follow, of course, to make these fully premixed systems stable. So we developed a couple of boilers where we decreased the equivalence ratio, so increased the excess of air. But we also developed a few burners systems which are more nozzle mix type of burners to prevent flashback anyway. So it's always a bit dangerous with these systems because if something goes wrong, if the fuel to air ratio changes a little bit, then immediately you see a flashback, and that's something you basically do not want to have. But one of the solutions is to increase the excess of air to reduce the laminar burning velocity. Other systems, for example, also premixed, are partially premixed burners, like for example, used in the industry, but also domestic use. For example, hot water heaters often are partially premixed, but also cookers are partly premixed. And then the equivalence ratio is, of course, higher than 1. That's what you see here. If you add hydrogen, then you have a shift in the equivalence ratio, but also an increase in burning velocity because you simply change you add hydrogen. So it's a double effect, a shift in the equivalence ratio, but also hydrogen out of itself burns faster. And at a certain point, you also get flashback. If you look at the two pictures, the top picture is natural gas. So you see a nice blue flame far away from burner surface. But if you add hydrogen, then the flames become smaller. They start to stabilize on the burner surface. And around 70%, you see the picture below. And then you see that the flame is completely stabilized on the burner ports. And that's causing a lot of overheating. And if we add a little bit more hydrogen, then we get complete flashback of the flame back in the burner ports. So for these appliances, it's almost impossible to use pure hydrogen. We do not have solutions for it, but one of the solutions is just simply remove these appliances. But it's difficult to make pure hydrogen appliances for when using partially premixed systems. We developed a few cookers, for example, and there we developed a complete new system which was burning safe and very well, but not using the partially premixed ones. If we go to examples of non-premixed burners, just an example what we did in our lab. What we did, we tried to convert a forced draft burner to a pure, what is used for natural gas, to for mixers, blends with natural gas, hydrogen, but also converted to pure hydrogen. And this is just an example. This is a simple hot water boiler. I think it's around half a megawatt, 475 kilowatts. And what we did, we converted this system completely to flexible hydrogen concentrations. What was the demand of the industry? They asked us, can you develop a burner which we can use for natural gas, mixtures of hydrogen, but also for pure hydrogen? So what we did, we changed the ionization probe, which is used as flame detection system for this boiler. If you switch to hydrogen, then you do not produce enough ions anymore in the flame, so that system does not work. So we replaced it by using a UV sensor, and that one worked very well for sensing pure hydrogen. We also developed a fuel adaptive control system. I will show that on the next page, but first, to give you an impression about the burner we use, it's just a simple but very good forced draft burner system. As you can see here, you have a disc with all kind of small holes where water flow, where the combustion air flows through, but also the combustion air flows around it, as you can see here on the air annulus. And fuel is flown perpendicular to the airflow, so to get good mixing. And in the middle, you always have also a kind of pilot flame, which is always burning. That's how the burner system works. And what we did, we included a simple system in order to always keep the power constant, but also to keep the fuel air ratio constant upon hydrogen addition. So basically we measure with a sensor the hydrogen content in the natural gas, and we also measure the Wobbe index of the natural gas. And based on that, we tune the fuel to air ratio in such a way that we always have the same power output, but also always have the same equivalence ratio, a lambda in our combustion. Some results, and that's shown here. If you look at the bottom, then you see the flame images we took. For example, for this flame, we added hydrogen up to 100%. And then what you see is, of course, the flame color changes from blue, and at a certain point it becomes an orange kind of color. It's typically for these flames that we use for hydrogen. But what we also observed is that the flame length did not change that much, and also the flame width for these kind of flames did not change that much when we switch from natural gas to hydrogen. Of course, when we use the control system, if we do not use a control system, then you see that the oxygen in the flue gases increases when you increase the amount of hydrogen. And when we switch back to complete hydrogen, then it falls back to the normal value, which follows basically the Wobbe index. And the same you see for the thermal input. But when we use the control system, then we are able to keep the oxygen content more or less constant in the flue gases. And also we are keeping the thermal input more or less constant. You always see some fluctuations, but that's due to the fluctuations of the valve system used, which is always giving some fluctuations, of course. If you then look at the NOx emission, and that's the major issue we have with this burner, so it burns very stable. However, the NOx emission, as you can see here, increases drastically. We saw a factor of 3 increase when we switched from natural gas here to pure hydrogen here. And that's so from 70, that's a legal limit in the Netherlands, to around 210 milligrams per cubic meter. So that's a huge increase, and that's something you do not want, of course. So we try to do to perform several NOx mitigating strategies. For example, changing the fuel to air ratio, but as you can see here, that does not affect that much. Was even when we increase the excess air ratio, then the NOx emission increased in our case. So we tried a different method, and that's quite known for the experts, I think, using external flue gas recirculation. So what we did, a part of the flue gases, we brought back to the combustion air inlet. So we diluted basically the combustion air with inert molecules. And for that, you reduce the flame temperature, and then also you see a quite steep drop in the NOx emission. So at a certain point, we were below the NOx emissions from natural gas. And the advantage of hydrogen is that you have a very stable combustion, very fast combustion. So you can add quite a lot of flue gases while maintaining a stable flame. So this was a very successful method by applying external flue gas recirculation to reduce the NOx emission for this kind of burner. So that's high temperature, low temperature processes. We also focused on high temperature processes. For example, we have a kiln in our furnace in our lab. To give you some flavor, the kiln contains quite a lot of windows, and the opposite side we also have these windows. So we shoot some laser beams through the furnace to measure the temperature in the kiln in situ, but also to measure oxygen, CO, and water concentrations in situ. And we have flue gas analyzers to measure the composition of the flue gases as well. We can do preheating up to around 600 degrees Celsius. And we installed also some cooling floors in the kiln in order to measure the heat flux, the amount of heat transferred from the flame to the cooling floors. One is below the flame and the other one is far away from the flame. And we can blend in quite a lot of gas compositions in order to see the effect of changing of gas compositions on the combustion behavior. Yeah, to give you some ideas, for example, one of the projects we have been running is by using an incinerator burner. If you look at the burner, this is the burner head, as you can see here. So if you look at these holes, there you see the air is coming out, and the holes in the middle there, the fuel is coming out. And you see already on the shape of the holes here that you have some kind of swirl you create by using this burner in order to get better mixing of the fuel and air. So this is a diffusion type of burner, so a nozzle mix burner. And we tested it at 100 and 200 kilowatts. And we tested the NOx behavior, but we also looked at the flame shape, for example, what happens when you add hydrogen to these kind of burner systems. One of the interesting things we observed for this burner when we added hydrogen, that you can see on the pictures below, is that when we added around 20% hydrogen up to 50, then the flame started to get really yellow. So you create a lot of soot formation when you add, for example, 50% hydrogen, as you can see here, to natural gas. First thing we thought, hey, that's strange, we get soot formation while we add hydrogen. So the CH ratio changes in a positive way, so you would not expect any soot. However, what happens is that the hydrogen molecules are diffusing quite fast to the outside regions, meet the oxygen molecules and consume all oxygen molecules present. And then when methane is there, then you have a lack of oxygen, and that's producing most probably the soot. In the exhaust, the soot fortunately is already gone, is already back converted to CO2, fortunately. But we see a very bright color when we switched when we added 50% hydrogen. That was quite interesting, and we saw also some other examples in the literature who saw actually the same as you can see on the picture above. Here you also start with a natural gas flame, a nice blue flame, no soot formation. However, when they added 50% hydrogen, then they also measured quite a lot of soot. So it's basically similar what we saw in our furnace. We also measured here the NOx emission. That's what you can see here on the top left. What you see is that here we measured an increase of around a factor of 2. Again, for low fractions of hydrogen up to 30–40%, you do not see a large increase in NOx. But if you switch completely to hydrogen, then here we saw a factor of 2 increase. And then you already see it. So it depends also on the burner type, how much NOx extra you will produce when you switch from natural gas to hydrogen. In this case, we reduced the NOx by including some inerts to the hydrogen blend to mimic flue gas recirculation, that's what you see on the picture on the right-hand side. And then you see the more nitrogen you add, the lower the NOx emission. However, currently what we are aiming for is to develop also burners which have internal flue gas recirculations in order to reduce the NOx emission, because often for high temperature processes, it's unwanted to use external flue gas recirculation. So it's better to create internal flue gas recirculation. Some other project examples. Currently, we're running a quite big industry project with 40 partners. All along the gas value chain, like gas producing companies like Equinor, but also end users like Tata. And we have quite a lot of burner manufacturers that are involved, such as, for example, Honeywell. And there we test quite a lot of burners. We test in total 5 air burners, industrial air burners, 1 oxy-fuel burner we just finished. And we developed also a new concept, H2, where you can burn pure hydrogen oxygen in a steam boiler. And there we add some water vapor in order to get a stable combustion. That's currently work which is currently going on, which we do together with Stoic Thermic. An example, and I really like this one. Here you see a flame on the left-hand side, it's natural gas. Like we already mentioned, if you switch to hydrogen combustion, then the hot flame zone is crawling more downstream to the burner surface. It's basically the hot zone is getting closer to the burner surface. And as a result, what you can see here, we have a ceramic tube, that's the black tube. But if we switch to hydrogen combustion, then you see that the black tube becomes really hot. It becomes orange color. So it becomes around 1000 degrees Celsius or 800 degrees Celsius. So you get a lot more heat is produced already inside of the ceramic tube when you switch to hydrogen combustion. And I'm not saying that the ceramic tube will be damaged, but maybe on the long term it can also have some effects. Another effect is, of course, if the hot zone crawls closer to the burner surface, is also that the burner block gets hotter. And on the long term, also these effects should be studied in more detail, of course. And what we're currently doing is making flame images of the flames. So we, for example, have an infrared camera. Normally, those are tuned for CO2 molecules to measure the temperature differences in the flame. But in this case, we had a prototype, and there we used the water lines in order to get flame images from this camera. And as you can see, you get quite nice pictures of the flame shape. And we do this project together with Celsius, and they do the CFD modeling. So hopefully, maybe in some months, we can show more detailed results of the project. But we also see again that the NOx emission for most of these burners increases. And we also see for some of the burners tested that we have changes in flame length, and that depends strongly on the type of burner used. We tested some swirl burners, and now we're testing more pipe, kind of pipe-in-pipe burners. And then you see also differences in the flame shape upon hydrogen addition. And we also measure, for example, by using radiation flux sensors, the radiation from the flames. And what we measured thus far is that we do not see that much difference between the radiation coming from a hydrogen flame in comparison to a natural gas flame. Other tests we are currently performing and also did. At the beginning of the year, we did together with Flametech and Lindegas for the Glass Future project, we tested some oxy-fuel flames, as you can see here. So there we used 2 dedicated oxy-fuel burners, and both burners worked very well. So based on that, you also can say, okay, we also can use oxy-fuel combustion, pure hydrogen oxygen combustion, and that might also be beneficial, because if you have electrolysis, then you produce hydrogen and also oxygen, so that will increase your efficiency. So that this might also be a solution for the future. And currently we're testing now an air liquide burner, also for mixtures of methane and hydrogen and pure hydrogen, to see if we can use one oxy-fuel burner for all those kind of mixtures. And we just finished those tests within the project as well. We are currently running one pilot project based on the experiments we did on the boiler. We are running now at Netmag, an industry in the Netherlands. We are converting an oil furnace, it's a 2 megawatt furnace. And that one should also be fueled with natural gas, blends of hydrogen and pure hydrogen. And I think in the beginning of next month, the pilot will start. The pilot already started, but then we will start burning those mixtures. So everything is now prepared. So we're looking forward to see the research also in practice in this case. Well, the next phase, like I already mentioned, I think for the next decade, there's a lot of work to do for us combustion researchers. One of the things is, of course, optimizing burners, optimizing heat transfer, reducing NOx emissions, but also developing safety protocols for the industry. And I think also what's very important is studying the impact of when you switch from natural gas to hydrogen on product quality, like for example, glass making, but also on the refractory material. So that's relevant, like I said, glass, steel industry, ceramics. So in my opinion, we still have a lot of work to investigate together as researchers in the field of combustion. Well, thank you very much for your attention.
Yes, indeed.
Questions, I think. For Martijn.